but I am telling you right now, that motherfucker back there is not real.
Complex numbers are actually not that complex. Even if you're completely retarded, you can look like a genius because you can solve for non-real roots. It's basically just GCSE surds and algebra, except we're using new numbers. In maths, you can sort numbers into groups called sets. First is the natural number set.
Hey, no, stop, just calm down, don't do it.
These are basically the normal numbers you count with.
These people crash cars.
Basically year 2 level maths. They can't exactly count with negative numbers. This set of numbers is the integers. Now if you go past whole numbers and start using fractions, you get rational numbers. Fancy Q for quotient. These can be expressed as A over B, where A and B are.
Integers and B is non-zero.
But then you get numbers which aren't able to be expressed as A over B, like root 2. There, I just proved it. They're still on the number line, so these are called real numbers. Now with normal A-level maths you're done here. If you see anything that's outside of the real numbers, you just put a massive X and then say no real solutions.
No. No. Mm-mm. Mm-mm. No. 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 Hell no. 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 I refuse. No. No.
But with further maths you go beyond this. Whenever you see negative square roots, it means it's in the set of imaginary numbers. That's because there's no real number that squares to give a negative. It's so easy to turn negative square roots into imaginary numbers. Just split it up into the square root of a number times the square root of -1. Now you can just change the square root of -1 to I. And that's basically it. That's all you have now. All imaginary numbers are in the form bi, where b is a real coefficient of I. What if you combine a real number with an imaginary number? Seems kinda complex, huh?
Oh, brother, this guy stinks!
Now we have the set of complex numbers. This is basically the same as normal algebra, where instead of x, you have I. They don't mix together. Real and imaginary numbers don't mix. So complex numbers are in the form a plus bi, where a and b are real numbers. Normally we represent real numbers with the letter x, but with complex numbers, we use the letter z. I strongly recommend you start writing your z's with dashes through the middle. Otherwise you will get them mixed up with your 2's. It took me a while to get used to it, but it's very worth it in the end. Complex numbers have 2 parts to them, a real component and an imaginary component. For instance, with z equals 3 plus 2i, the real component of z is 3, and the imaginary component of z is 2. Now if the real component of z is 0, the number is purely imaginary. If the imaginary component of z is 0, the number is purely real. Adding and subtracting complex numbers is basically the exact same as algebra. You just collect the like terms. The real components with the real components and the imaginary components with the imaginary components. Multiplying. Multiplying is also the same with algebra, except it's got to know that I squared is -1. Now sometimes you'll get higher than I squared, like I cubed, I to the 4, but all you got to know is whenever I is raised to a positive power, you can either get I minus I, 1 or -1. Okay, so here's the rules that shows what powers give what. Fairly intuitive once you know that it follows a pattern of 4 and it just repeats. So now you can find out what I to any power is. So for instance, if I said I to the power of 307, 307 is 1 before a multiple of 4, so therefore it has to be minus I. Dividing by imaginary numbers. You want to treat them exactly like surds, because they are. So normally you know that you don't like surds at the bottom of a fraction. So to get rid of it, you rationalize the denominator. But if you have an imaginary number at the bottom of a fraction, we want to realize the denominator. So you do the exact same process as rationalizing, multiply by the surd component, in this case it's going to be I, then simplify, and that's it. Now if you have a complex number instead of just an imaginary number, you also treat it exactly like a surd. So you multiply by its conjugate, so now you can use difference of 2 squares. But it's slightly different with complex numbers, because look what happens when you have a plus bi multiplied by a minus bi. So according to difference of 2 squares, it's just going to be a squared minus b squared I squared, but we know that I squared is the same as -1. So then it simplifies to a squared plus b squared. So going back to this example, it's just going to be 3 squared plus 2 squared, so 9 plus 4, which is 13. Okay, so the last bit in chapter 1 is a bit weird because it's kind of long unless you use methods from chapter 4. And since you're going to have to learn that anyway, you might as well just use it now. Okay, first of all, I'm just going to assume you know factor theorem, since this is the slightly more advanced version of it. If not, that's tough. Okay, first we're going to look at a question which gives you one real root. Here it gives us that 2 is a real root. So the method for these questions is factorize and solve. So since we know that f of 2 equals 0, and obviously to show that you just plug it in, and that implies that z minus 2 is a factor of f of z. This is where you'd use long division if you wanted to dilly-dally, but if you're a real G with places to be, then you'll factorize it in your head. So here we have a linear term, and we want some quadratic to go with it. We don't know what the coefficients are yet, so we just need to figure out what numbers to put in, and this needs to give us the original equation. So let's start from the ends because this is always the easiest. Okay, so how can we make a z cubed? Well, we can do z times 1 z squared. So this is going to be a 1, but actually we could just leave that as nothing. And let's look at the other end. So we've got minus 26. How can we make a minus 26? Well, we have to do a constant times a constant. So minus 2 times something gives minus 26, and that will be plus 13. Okay, so now we can either look at this or this. It doesn't really matter. So let's just look at minus 6 z squared. So we want two things to add up to minus 6 z squared. Well, we already have one thing from minus 2 times z squared. That gives us minus 2z squared. So now we need something else to give us our minus 6z squared. And that's going to be z times the z. So clearly we want this to be minus 4z squared here. And the way we get minus 4 from this purple bit is by doing z times minus 4z. And you see it also works with the 21z. Now we already had 13z from this sum here. Then we needed to add another 8z to get our 21, which we could have done by doing minus 2 times minus 4z. So now we just solve this quadratic. So let's just complete the square. So from here I'd just like to write z equals, and imagine we're bringing this to the other side of the equal sign, so this becomes a 2, and of course this becomes a minus 9, and then we have to square root it. So this becomes plus minus 3i. And we also had z equals 2 from before. So then this gives us all 3 of our roots. Now that may have been a bit confusing, but I'm going to do it quick just to show you how I'd normally do it. Okay, so here z equals 3 is a root, so that means z minus 3 is a factor. So that means g of z equals z minus 3 times some quadratic. And here we've got a 2z cubed here, so this means this has to be 2z squared. We have a minus 3 here, so that means the constant at the end is going to have to be a plus 1. And let's look at this minus 5z. So we already have 1z right here, so we need another minus 6z to get to minus 5. And the way we can do that is adding a 2z here. And of course you can check that z squared term, so we have a minus 6z here, then we add on 2z squared there, and that gives us our minus 4z squared, so we know it's right. Then of course solving this quadratic, we can just half everything, complete the square. So we brought that over, which means there's a minus half, and we brought this over and square rooted it, so that means it's going to be plus minus half I. And of course our root from before, which was z is 3. So notice how we started with a cubic here, and we ended up with 3 roots. Same thing here, we started with cubic, and we also got 3 roots. So the highest power of a polynomial which has a non-zero coefficient, the solution to that polynomial will have exactly n roots. Not all of them have to be real. Any polynomial can be factorized into linear terms and non-reducible quadratics, which means you can't just factorize this normally. So with this question, it gives us a complex root. So for this, what we do is find the conjugate root, construct the quadratic the 2 roots came from, then factorize and solve. So here it tells us that one of the roots is minus 4 plus I, and I just called that alpha. Another root, beta, this is going to be minus 4 minus I. And of course this makes sense if you think of the quadratic formula, it has that plus minus bit, and that refers to that bit. Okay, so now we have 2 roots. What we can do is construct a quadratic from it. And what the textbook would have you do is put it into this form, and from this you can see where the roots came from, and then expand it, which is just long. There's no need. So instead, let's just replace this with alpha and replace this with beta. So if you expand it, you get z squared beta z minus alpha z plus alpha beta. We can factorize out that z, which gives us z squared minus alpha plus beta z plus alpha beta equals 0. And now you could see how this relates to a more general equation. So our z coefficient is going to be this, and our constant term is going to be this. So this is how the roots of the equation relate to the actual equation itself. And you go into way more detail in chapter 4, of course. Oh, but what about the a? Just assume it's 1, man, because everything else can scale accordingly. Like for instance, if we had 2z squared plus 3z plus 1 equals 0, here you could say that, oh, a is not 1. Oh, you can make it 1. These 2 equations are the same. So we can just ignore a for now. Okay, so now we have our 2 roots. Let's make a quadratic from it. So our b term is going to be the negative of the sum of these two. When you add these up, the imaginary parts will always cancel out because they're conjugates. And now these parts you just add together, so minus 4 plus minus 4 is just minus 8. Of course we're doing minus 8. Then for our c term we're doing alpha beta, which is going to be minus 4 plus I minus 4 minus I. Difference is 2 squares like we covered before. Minus 4 squared plus 1 squared, and that's going to be 17. So that means we have our quadratic, which is z squared plus 8z plus 17. Now this is a factor of our original equation, right? So now we need to figure out what we need to multiply this by to get to our original equation. Here we have a z cubed, which means we're going to have a z in here. And this is quite easy since it's linear. We only have one term left, which is the constant. So minus 68, we have a 17 here. That means we have to put minus 4. Now to get our last remaining root, we just solve this bit. So z is 4. Then we had the bit from before, which is minus 4 plus minus I.